And next and last, we have Gan, who's going to talk about verified library level choreographic programming with algebraic effects.
Check. Everyone hear me right? Okay, thanks for the introduction. Hi, everyone. I'm Shen, and I'm excited to tell you about toward verified library level choreographic programming with algebraic effects. That's a pretty long title. And this is the last talk of the last session. I guess people might feel a bit overwhelmed by the so many great talks we've had so far. So as the title suggests, our paper is about doing choreographic programming with algebraic effects and proving its correctness, all in the proof assistant Agda. But at this point, I guess people are tired, and I want to, and don't want to see hundreds of Agda code. So instead, I'm going to present a different view of our paper, which will just be choreographic programming with algebraic effects. Here's the main point I want to convey. I think algebraic effects are a viable mechanism for implementing a choreography language, and I want to advocate their use in our community. So of course, this needs a bit more explanation. So why do I think algebraic effects are a viable mechanism? There are three reasons. First, a choreography language built with algebraic effects is lightweight. The language is just a library. Unlike standalone implementations, we do not need to write a custom parser or compiler, which might require a significant amount of engineering. Second, the library implemented in this way is very concise. The code follows how we define things mathematically on paper. As the demonstration later in this talk indicates, the core functionality of a choreography language only takes less than 100 lines of code. Third, algebraic effects provide interoperability between the choreography language and the host language in which we implement it. This allows the choreography language to inherit rich ecosystems such as programming features, IDE support, and third-party libraries from the host language. A question you might want to ask now is, why algebraic effects? Especially at the end of this session, we have seen quite a few different ways to implement a library-level choreography language. So how do algebraic effects compare to them? Do algebraic effects bring anything new to the table? I think there's three reasons why I want to do this with algebraic effects. First, I think algebraic effects generalize previous library-level choreography language implementations. So two of the previous implementations that I have experience with are Haskell, which uses freer monads as its core mechanism, and Cruz, which is built on the idea of dependency injection. Having experienced both systems, I found there's something common with them. In a way, both systems define a choreography as a program with user-defined operations, and then endpoint projection gives those operation location-specific semantics. This is exactly the pattern of programming with algebraic effects. One defines uninterpreted effects and separately gives them semantics through effect handlers. Second, I think algebraic effects crystallize the core idea of library-level choreography programming. This is kind of related to the first point. Even though Haskell and Chorus share the core idea, they look very different on the surface due to the low-level details of freer monads and the dependency injection. This makes it hard for people to appreciate the core idea behind them. I think algebraic effects solve this problem by providing a simple interface to programming with effects, thus really crystallizing the core idea. Third, as a useful programming feature, algebraic effects are going mainstream as more and more languages are considering adapting them. For example, the WebAssembly community group is considering effect handlers as one of the mechanisms for supporting concurrency, asynchronous I/O, and the generators. So here we want to follow the trend and bring choreographic programming to a much broader audience. Okay, so that's some high-level points about choreographic programming with algebraic effects. Let's try to make these points a little bit more concrete. In the rest of this talk, I will demonstrate how to use OCaml, which recently added native support for effect handlers to build a library-level choreography language. Our choice of OCaml is inconsequential. The exact implementation strategy can be applied to other languages that support algebraic effects as well. And as a side note, effect handlers and algebraic algebraic effects are kind of synonyms, and I will use them interchangeably in the rest of this talk. So to begin with, let's first have a brief introduction to algebraic effects in OCaml. So algebraic effects in OCaml comprise mainly two parts: uninterpreted effects and effect handlers. Here, we are going to show an example. We will use algebraic effects to model stateful computations where we can write and read from a single storage. First, we declare the set of needed effects by extending the extensible variable type effect t from OCaml's standard library. So this effect t is defined as a generalized algebraic data type, or GADT for short. It has a type parameter denoted by the underscore, and each constructor is allowed to instantiate to a different type. We extend effect t with two new constructors, get and put. The declaration says the get effect takes no argument and returns an integer, and the put effect takes an integer argument and returns a unit. With the effect declaration, we can write some computations that perform those effects. Here's a function that reads the integer from the storage, writes back it times 2, we read the storage and print out the result. Next, we can write an effect handler that handles effects performed by a computation. We will handle a stateful computation as a state transforming function, the standard functional interpretation. An effect handler in OCaml is a record with 3 fields, a return case for handling pure values returned from the computation, an exception case for handling exceptions raised from the computation, and the most important part, an effect case for handling effects. Let's take a close look at the effect case. It is a function taking in an effect and returning an optional handling clause. Here we are saying that we will handle the get and the put effect and ignore others. For each effect, the handling clause is provided with a continuation k, which represents the remaining program after the effect is handled. For the get effect, we continue with the state from the context and execute the remaining computation with the same state. Similarly, for the put effect, we continue with a unit and execute the remaining program with the new state. We don't need to read all of this in detail. Here, I'm just trying to give you a feeling of what programming with effect handler is like. So finally, we use the match-with function to put everything together. The match-with function runs a computation. When the effect is performed, it captures the remaining program as a continuation, jumps out of it to the effect handler, and execute the corresponding handling clause supplied with the computation. In a way, effect handlers can be seen as a generalization of exception handlers. Similar to exception handlers, they allow control flow to jump out of the current execution context. Unlike exception handlers, effect handlers are also provided with a continuation, allowing them to return to where they left off. So this concludes the set of APIs one needs to know to use algebraic effects in OCaml. Now let's move on to see how to implement a choreography language with this feature. The first thing we need to figure out is the effect that a choreography can have. The most fundamental effect, obviously, is com, which describes an instance of communication between two locations. So here, we extend effect.t with a new constructor com. The com constructor takes two locations representing the sender and the receiver, respectively, a message of arbitrary type A marked as lazy, and returns a located value of type A. So here, lock is our location type. It can be as simple as plain strings or anything with decidable equality. The message is marked as lazy by using the lazy t type from OCaml to delay its evaluation. Because OCaml is an eager language, all arguments are evaluated before a function or constructor is called. Making message lazy allows the endpoint projection to selectively evaluate them as needed, which we will see in a moment. We could also have achieved the same thing by wrapping the message in a dummy function, but using the lazy t type makes the intention much more explicit. The com effect returns a located value of type A. So what are they? A located value represents a value at a specific location. It is similar to an optional value. It is either present with a value of type A or absent. Within a choreography, we have the implicit guarantee that a located value is always present for the receiver of com. Otherwise, it is absent. We provide an unwrap function to extract the value from a present located value and raise an exception if it's absent. Note that it's the programmer's responsibility to ensure a choreography only calls unwrap on a present located value. In a typical choreography language, we would like to enforce this statically using a type system or similar techniques. However, here, for simplicity, we leave that out. Next, we define two helper functions for performing the COM effect. The locally function executes a piece of code locally. It is defined as performing the COM effect with the sender and receiver being the same. The COM function is just a sync wrapper to the uppercase COM constructor. Now we can write some choreographies with the functions we have defined. Here is a distributed double function that involves two locations, Alice and Bob. First, Alice sends an integer they read from the standard input to Bob. Then Bob unwraps the integer, times it by 2, and sends the result back to Alice. Finally, Alice unwraps the result and prints it out. Here, we use the lazy keyword to create a lazy value. The expression following the lazy keyword is not evaluated immediately. I want to highlight how much this looks like a choreography we define on paper. Here's a choreography excerpt from a recently published paper. I think it's actually Pirouette. You can see that the two programs share a very similar structure, minus some syntactic differences. On paper, we tend to write variable bindings on the right side, and COM is defined as an infix operator. OK, so our next job is to figure out how to define endpoint projection as effect handlers. So first, we will assume that there's a pair of functions send and receive for sending and receiving messages among locations. The exact implementation is irrelevant to our exposition. Next, we define the endpoint projection function EPP. EPP takes a choreography C and the location L, and the function body is a call to the match with function on C with an effect handler specific for L. For the return case, we simply return the result, and for the exception case, we propagate the exception to the outside. The most interesting part is the effect case. Let's take a close look at them. So there's only one effect we need to deal with, the COM effect. Here, we are supplied with the sender and the receiver locations, a delayed message, and the continuation K. If the target location is equal to the sender and the receiver, we handle this effect as a local computation. We evaluate the delayed message using the force function from OCaml and continue the rest of the program with the result. If the target location is equal to the sender, we handle this as a send. We send the forced message and continue with the absent located value. If the target location is only equal to the receiver, we handle this effect as a receive. We call the receive function, get a result, and continue the rest of the program with that. Finally, if the target location is not equal to either the sender or the receiver, we handle this effect as a no op. We continue the rest of the program with absent located value. Now we can execute the distributed double program like this. OK, so far so good. Looks pretty simple, right? But there's an elephant in the room. What about conditionals? As people here know, conditionals are notoriously hard in choreographic programming because nodes need to be informed of the choice to decide what to do next. And we want to do this correctly and efficiently. In other words, inform and only inform nodes that need to know the choice. And also, we want to put the least burden on programmers in terms of annotations they have to write. Achieving the perfect balance between these three is not easy, and there's ongoing work on this, and we've heard a lot today. Here, I want to show algebraic effects enable fast prototyping by implementing recently proposed announce enclave-based conditionals using algebraic effects. So the choreography language we have implemented so far actually already support conditionals, but in a limited form. We can use OCaml's if then else, and everything seems to work if we don't branch on a located value. But things will go wrong if we try to branch on a located value, as it might not be present at all locations. So we can fix this by adding two new effects to our language, announce and enclave. Announce broadcasts a choice to a set of locations, so they can all branch on that. But some locations don't need to know the choice. They do not participate in any of the branches, or their behavior are not altered by the choice. So we introduce another effect, enclave, that carves out a sub-choreography and only execute it for a set of locations. With this design recipe in mind, we extend our effect with two new constructors. The announce effect is almost the same as com effect, except the receiver now can be a set of locations. The enclave effect takes a list of locations who will execute the sub-choreography. A sub-choreography returns some value of type A and returns a located value of type A. The endpoint projection for announce is, again, almost the same as com, except now we are dealing with a list of receivers. So if we are the sender, we need to iterate the send over the receiver list. The endpoint projection for enclave is also straightforward. If the target location is one of the locations participating in the enclave, we recursively call EPP on the sub-choreography and continue with the result of it. Otherwise, we continue with an absent located value. Of course, there's more improvements we can make here. For example, our implementation only allows a single location to announce the choice. But in practice, we might want to announce the choice transitively through multiple locations to take advantage of the network topology. We believe it's also doable with algebraic effects by introducing more effects. Here, the point is not to show a perfect way of doing conditionals, but to show algebraic effects enable fast and easy prototyping. So now we have reached the end of this talk. I'd like to discuss several things we are considering doing next. First, we want to keep growing the language, adding new features, and see if algebraic effects are up for the task. Second, we want to formalize this idea of choreographic programming with algebraic effects and prove its correctness, namely deadlock freedom. Most of the existing formalization is for standalone choreography languages, although there are some similarities between a standalone and a library-level choreography language. There are also some noticeable differences. For one thing, our library-level language has this notion of located values that's defined like an optional value, and it's critical for the correctness proof that they are used rightly. So it's worth developing a new formalization. Our paper contains an initial attempt at formalizing some of the ideas here in Agda, but there are still some ongoing parts. Last, we want to bring this idea of implementing choreographic programming to more languages with native support of algebraic effects. Thank you.
Thanks for the talk. Are there any questions? Jacopo, I'm going to let you in the queue for once.
So the com effect you talked about, it has this lazy component.
Mm-hmm.
So that's essentially a thunk.
Yes.
Can that? It looked like from the code that it can't, but I was wondering, can that itself do another communication when you run the lazy computation?
Right now, it can't.
So it would just be unhandled if it did.
Yes. Yeah. When we force the message, when we do the forcing, it's not provided with effect handler. So if you try to do com inside it, it's unhandled basically. Yeah. So
is that the behavior you want? I guess it may well be.
Yeah. Right now, I don't find like an application where I have to do another like a hierarchical choreography like here. No need here.
Well, one question is about performances. Do you think that by using effect handlers in a way we can reach performances of other languages?
It depends on how effect handlers are implemented in that language. So for OCaml, one thing I can tell is the performance is very good. It's almost as good as just calling the function directly. But there's some OCaml achieved this because because they constrain the way you use continuations. The continuation can be only used once, so they can sort of have some very efficient representation of continuation. But for languages where you want to use continuations more than one times, it might the performance might not be as good as a more direct implementation.
And that's an open question. Have you thought if these fat handlers can, in a way, be one of the ways to have fault tolerance for choreography? So if messages fails or things like this, can they be one of the ingredients to solve this issue?
So the question is how to deal with failures. So one way to deal with that is extend the type of comp to not returning a located value, but to returning a maybe located value with the nothing optional located value, with the non-case being that something bad has happened. I guess that's one way to do that.
So this is all in OCaml. You mentioned that you had an earlier Agda-based system that you started on. Do you anticipate a machine, and I guess you've also mentioned that there are various things that aren't checked by the type system right now.
Yes.
Do you expect a machine proof of correctness in this system?
Yes. In our Agda formalization, we actually have more fancier types. So located value are annotated with their location.
So this is not supplanting the Agda. This is in place of for today.
Yeah, I would say they are in parallel. The Agda is more theoretic focused. This one is more practical. So I don't want to. I could have do some type level tricks to type located value more precisely, but I figured just to make it simple and people understand. Yeah, so I left that one.
Okay. There are no more questions. Then we can thank the speaker again. And